All right, let's jump into example 2. So example 2, we have an airplane flying overhead at a constant elevation of 4,000 feet. A man is viewing from the plane from a position 3,000 feet from the base of a radio tower. The airplane is flying horizontally away from the man. If the plane is flying at the rate of 600 feet per second, at what rate is the distance between the man and the plane increasing when the plane passes over the radio tower? So we want to start by trying to get a picture of what this represents. So this is going to be my man, and then right here we're going to have my radio tower, and I'm just drawing the radio tower as a dot because the height of the tower isn't relevant to this problem. We have an airplane in the sky that is moving away from the man, traveling horizontally, and we also know that this airplane is a constant 4,000 feet in the sky. Now we are solving for the rate, the distance between the man and the airplane is changing. So here's our man, and if the airplane is above the radio tower, this is the distance here between the man and the airplane. So we're not actually looking for this distance so much as we're looking for the rate of this distance. And so we are going to call this a function, x of t. So this is the distance per unit of time that the distance between the man and the airplane is changing, if that makes sense. We also know that the plane is flying at a rate of 600 feet per second. And that's also a constant rate here. And then we know if the airplane is above the radio tower, then it is exactly 3,000 feet horizontally away from the man at that exact moment. So we have this horizontal distance, and I'm going to switch colors. Let's call that blue. So we know that this exact moment, when the airplane is above the radio tower, this is 3,000 feet. This is not a rate, and obviously as the airplane is moving away from the man, this distance is also changing. So what kind of equation are we looking at when we set this up? Well, I'm hoping from my picture, and you will be drawing your own pictures, but I'm hoping you can see this right triangle we've got going on. And at one exact moment, you can even see that it's a 3, 4, 5 triangle. But keep in mind, we're trying to write this as a related rate problem. So it's a constantly changing situation. Well, let's bring back our Pythagorean theorem. There we go. And so for our distances, the only constant we have is the 4,000 feet. That's not changing. The hypotenuse we've labeled as x of t. This is what we want to know. And we're actually going to need a new variable for the horizontal because, yes, at one exact moment, the horizontal distance between the airplane and the man is 3,000 feet. But the horizontal distance between the airplane and the man is not always 3,000 feet. So that is technically an unknown value when we begin our problem. So we've got horizontal distance with respect to time, vertical distance, technically it's with respect to time, but it is constant, and we've got our hypotenuse, or our distance between the airplane and the man. So from here, we're ready to move on to the derivative step. And we're going to be doing power rule, chain rule. We've got 2 h of t, dh dt. The derivative of a constant is just 0, so we'll just skim over that. And then we have 2 x of t dx dt. So let's go through each of these variables and what they mean in the context of the problem. H of t is the horizontal distance between the airplane and the man. dH dt is the speed at which the horizontal distance is changing. X of t is the hypotenuse, the distance between the airplane and the man. And dx dt is the speed at which that distance is changing. So dx dt is what we are solving for. Let's plug in what we know. We know that when the airplane is directly above the radio tower, the horizontal distance is 3,000. We also know that the airplane was flying at a horizontal speed of 600 feet per second. See if I can squeeze a unit in there. And we also had a times 2 that I don't want to drop. Equals 2 times the hypotenuse times dx dt, which we don't know, we are solving for. So that leaves us with this hypotenuse here, this x of t, and we have to know it, otherwise we're looking at two variables in our single equation. So here, if you're looking at this exact moment, and we talked about this for a brief second, we do know that the horizontal is 3,000, the vertical is 4,000, and we can actually use the Pythagorean theorem, to figure out that the hypotenuse is 5,000. So let's do this off to the side. We've got 3,000 squared plus 4,000 squared equals, and I'm going to say x of t squared. And that leaves us with 25, 2, 3, 6, so we got 25 million equals x of t squared. If you square root that, you get 5,000. All right, let's continue solving our problem. Over here on the left side, we have 2 times 3,000 times 600. Okay, and on the right-hand side, we have 2 times 5,000 dx dt. Dividing by 10,000, we're left with 360 feet per second equals dx dt. And so we have successfully solved our second example, which was to find the rate at which the distance between the airplane and man was changing when the airplane is above the radio tower.